All right, so 10.2 difference in sample means, here's the deal. Very much like 10.1, the difference in sample proportions. So we're going to use our same setup. So we're going to be looking at both confidence intervals and tests of significance in this. So let's talk about this. The two sample difference of means. Let's set this up, right? So it's similar to like what we did. So we got population 1. We're going to have population 2. We're going to pull out of this, we're going to pull a sample 1. We're going to pull out of this, we're going to pull out a sample 2, right? So we're always going to be comparing things. So this could be like the average SAT score of West Linn High School, the average SAT score of Lake Ridge High School, and we want to compare them. Who has better scores? Well, anytime that you're going to compare, we're going to subtract. So what we're really after in this entire thing is x bar 1 minus x bar 2 and see what we get here. Now, if we end up with a 0, we're going to say that they're the same. If we end up with something greater than 0, well, then the first sample must have been larger than the second sample. If you end up with something less than 0, well, then the first average must have been smaller than the second average, right? Those are just some algebraic facts, okay? So that's what we're doing. But then we're going to use this to hopefully estimate the true parameter, right? So what is going on in there? All right, so that's the idea. Same structure as we did for proportions. All right, so let's talk about confidence intervals. All right, confidence intervals. All right, parameter of interest. We want to know the difference in the means. That's what we're after, the true difference in the means of the two populations. So we're going to use our samples to do that. Assumptions. Just like we did for proportions, we have to go check the sample that came from population 1 and the sample that came from population 2. Now, on these, it is very unlikely to do a z-test. It's possible, but usually for means, we're going to be doing t-test. But to sample t-test, right? Because we're taking a sample from each population. So we're always going to be looking for is N1 greater than or equal to 30? If it is, t-distribution is robust. All right. And then you're going to do the same thing. Is the second sample greater than 30? If so, the t-distribution is robust. And we move on. What if n is less than 30? Look at the graph. Remember, we want to see no outliers in the first data set. Oops, I should put a 1 there. And 2, if it's less than 30, got to do the same thing. Got to go physically look at it and see, is it look somewhat so like a t-distribution? No outliers, no strong skewness. All right, number 2, right? We're always going to look for random. Same thing there. Number 3, we're always going to kind of check the 10% rule for the first population, and we'll do the same thing there. All right. So remember, it is just more work to double up on these things. It's the same thing we've been doing in Chapter 8 and Chapter 9. We're doing it again in Chapter 10. Just continue to think, do it twice, because we got 2 populations. We need to make sure it's going to work out of both of those. All right. Talk about the naming I'm going to do. So I'm actually going to talk about what is my calculator function, right? So in our calculator, we have a thing called sample t-test, right? So I'm going to go my calculator stat test sample t-test. Now there is also, don't fret, there is a sample z-test in case they give us the population standard deviations. Very rare to use. Most likely you're going to be here, but that's all going to just matter on what they give you. All right. So that's what we're going to end up using. Interval calculation. Let's talk it through here. So by formula, this is a great place to go to our formula sheet and check the true difference of means if we have that available to us. So pulling from my formula sheet, remember it's attached in your Google Classroom. Go ahead and click on that, pull that up. Go all the way down to where it says for two populations, x bar 1 minus x bar 2. Slide all the way across underneath where it says standard error, because we're actually putting in the little sample standard deviations on those things, right? So we're going to kind of put that together, but with the rest of it. So if you want to just write it out here, that's going to be great. So here's what it's going to look like. X bar 1 minus x bar 2, right? So there's that first part. That's the difference in the samples, plus or minus. Since we know we're doing a t, we're going to go look up a t critical value, okay? And then after that, I need that standard error calculation, which is just the standard deviation. The reason we call it standard error is because we put sample stuff in it, right? So it is change to variance for the first one, squared, right? And then add to it, change the second one to variance, add those together and square root it, give us back to standard deviation. Remember, we did that back in chapter 6, if you recall. So this is going to be it right here. Now, let's talk real quick degree of freedom, because it gets a little tricky here. So degree of freedom is a super complex formula for a two sample difference. So what we're going to do is one of two things, okay, when we're doing this. We are going to degree of freedom, let the calculator find it for us, or go ahead and write this down. We have what we call the conservative method. And it is very conservative. But what you're going to do is take the smaller of the two samples and use its degree of freedom. And again, it's a conservative method, and it will produce a degree of freedom a lot smaller than the one that your calculator will give for us. Now, the one the calculator will give for us will probably be a decimal. So that's okay if it's a decimal. Just go look it up on the t-table like we always do, right? So the t-table, and we're always going to use the more conservative number that comes off the t-table. So we'll do one of those. But let's go ahead and write this formula down so that you got it. All right. So there's that. And in the conclusion, it's going to sound very similar to it did with proportions. We are blank % confident that the true difference in proportions is contained in the interval that we calculate. Okay. So I'm not going to write that out, but you'll see it come through. All right. Let's talk phantoms. Okay, so as we transition to test of significance, right? Test of significance. Then what we're going to want to do is just think through the different parts that are really important to us. Okay, so null hypothesis is always going to be, we are always going to make the standard claim that the first population mean is equal to the second population mean. Or another way to write it is that population 1 minus population 2 mean is equal to 0. So there's no difference in the mean. Alternative hypothesis, we're just going to use greater than, less than, or not equals to sign in there. But here you go. This is a standard. You don't even have to think too hard about what it is. Just know that's what we're going to be plugging in. Assumptions, we just listed them above. Use the same that we did above. Right, naming what we're doing on this one. Remember, in your calculator, you're going to use the two sample t test. There is also a z-test in case those rare occasions happen. But you're not going to find too often that that happens. Draw the curve, shade the curve, all that stuff, right? Show the t-score. So here we go. It's going to be this, and my curve is always going to be centered around 0. Why? Because the claim is that the difference is 0. So we're going to always center it around as if the difference is 0, and then we're going to find out where our difference in our sample means are. And then you're always going to shade more extreme, right, when you do that. Make a decision, just like we've always made a decision, alpha versus p-level. You got it. Summarize, just like we've always summarized. All right? Hopefully that gets you on the right track right there. All right, so with that, let's just take a moment and look at an example that's going to go right alongside this thing here. Okay, so I got example 1 and 2 here because we're going to try to mix these ideas of a panic problem versus a phantoms problem, right? So that's what some of the pieces will be. So reading through this one, Jordan's cat Fern is a finicky eater. Jordan is trying to determine which of the 2 brands of canned cat food Fern prefers, Tabcat or Chow Lion. For 2 months, she flips a coin in each day to decide which of the 2 foods to feed Fern and weighs how much Fern eats in grams. All right, so here we go, guys. So I'm going to tell you right off the bat that Tabcat and Chow Lion, those are 2 different populations, right? 2 different styles of foods, right? So we're taking samples, right, of each one. So we know that we have a 2 sample something going on here. Now, right off the bat, I see a mean and I see a standard deviation for each. Therefore, this is the means problem, all right? So let's find the standard error of the difference in means amount Tabcat that Fern eats and the mean amount Chow Lion she eats. So here's the deal, guys, is if we are doing standard error, that sounds like standard deviation. It's just when we replace the population something with the sample something. So that then it becomes error instead of deviation. So let's check our formula sheet. If you got your formula sheet, let's go to it, because remember, we were working with some proportions earlier, right? So we have stepped into this realm here, but let's just move down to means, and we're here 2 populations. Let me highlight what I'm talking about here. For 2 populations, we are thinking about all of these things here. All right, so let's go here. Now notice, again, here's what we got. Here is the standard deviation for the difference in means. This over here, this is called the standard error for the standard or the sample difference, right? Notice the only difference is, and I can show you, right? It's instead of population, it's sample. Instead of population, it's sample. Then we call it standard error instead of standard deviation. Otherwise, it's the same thing. So literally, this is what they want us to write over here. Only we're going to write it with the actual appropriate values in there. Okay, so you ready? Here's what it looks like. The square root, the giant square root of Tabcat and the mean amount of Chow Lion. So I'm going to do Tabcat first. 3.45, that's the standard deviation squared to make it a variance, divided by its sample size, 31, plus 4.62 squared to make it a variance, divided by 30, its sample size. And then square root it, and you get back down to the standard deviation, or in this case, standard error, because we used that piece on it, right? So let's make sure that we have that all dialed in. All right, part B, construct and interpret a 99% confidence interval for the difference in mean amount of food Fern eats when she is offered Tabcat and when she is offered Chow Lion. So the difference in the 2, right? So thinking about confidence interval. When you hear confidence interval, what do you think? Panic? Yes, that's what you should think. And what is the things that we need to be able to put the A, the I, the C? All right, the assumption checks, right? What are the assumption checks? Well, we need to make sure that Tabcat and Chow Lion both are available for us to use, right? So I'm going to tell you right now, this is a t distribution because the only numbers that we have to go off are standard deviation of the sample, not of the population. So these are t distributions. So we need to be sure, is it appropriate to use a t distribution? Tabcat, n equals 31. So we're going to say t distribution is robust. chow line, n is equal to 30. So we hit our minimums barely. T-distribution is robust. So guess what? When we subtract Tabby Cat and chow lion, we're going to be able to use a T-distribution. So that's good. Let's see. She flips a coin. So coin flip. So random. Perfect, right? So we know that we tried to keep it unbiased by keeping it random. And then 10% rule or independence, right? So it's actually independent because each day is different and the food's not going to affect it. But in case you want to use 10% rule, that's totally fine. You can use 10% rule, right? So we can say total days. Is there more than 310 days to use? Total days on this one, is there more than 300 days to use, right? Absolutely, right? We can use, there's an infinite amount of days, which is why this is considered independent, because we're not just snagging some days out of a limited population. This is an infinite population, the amount of days that she can use. All right, there's that. All right, let's do the interval calculation. All right, interval calculation. Here's what, if you need to write it down, let's write it down generically. X1 minus X bar 2, sorry, X bar, plus or minus, we're talking about a T critical value, right? Remember, we're going to have to find that here in a second. And then we're going to use that big old standard error, standard deviation calculation. So it's the first one plus change the second one to variance divided by N2. Perfect. There we go. Okay. Now let's put actual numbers in these from the data set above. So it's 85.2 minus 82.1 plus or minus T star. We'll go look that up in just a second. And let's do 3.45 squared over 31 plus 4.62 squared over 30. All right, T star. We need to go look that up, but I will look that up after the fact. So I'm going to let my calculator also give me this. So in your calculators, if you will, let's go to stat, let's go to tests, let's go to sample. Let me see if it says sample or just sam. To samp T interval. Again, T because we are doing T distributions and not normal. To sample T interval. Interval, right? Right now we're doing the interval. Later on we'll do the test. Do we have data? Do we have stats? We have stats to put in here. X bar 1, 85.2. S1, 3.45. Sample size, 31. Okay, go to the second one, 82.1. Standard deviation, 4.62. And sample size, 30. Confidence level, 99.99. Okay, it's saying pooled. It's saying pooled. I want you to know that we will not be doing any pooled samples, right? And this is, so what pooled means, right? So like sometimes like this right here versus this is called a pooled. This is pooled for proportions. Right? It's pooled. Pooled means we're gonna assume that they're the same. We're gonna pull them together. So this one right here, we're just gonna always say no to pool. Okay. So if you need to put that little claim right now, this is the AP level. Just say no to pooled. Okay. So just say no to pooled, and then let's go and calculate that. Okay. So it's going to give us a couple different crazy things here. First thing I'm going to do, though, is just write this 0.30484, and I get 5.8952, right? So that's what I get there. But guess what else they give me? They give me a degree. I'm going to write this thing out here. Degree of freedom equals 53.64, okay? So remember, if your calculator gives you a degree of freedom, use it. If they didn't give me a degree of freedom and I wanted to use the conservative, then I would use the smaller of the two sample sizes, which is 30, and take its degree of freedom. Degree of freedom equals 29. Notice how dramatically different those are, right? Now, since I'm using my calculator, I'm going to use this one and ignore the conservative. If I had to use a conservative and look it up by hand, then I would look it up by hand and do a conservative. Go with me now, if you will, to the t table, and we will look up that t value. Okay, so we got it here. Here's our t table, right? Now, again, our degree of freedom in this one is we're going to use this 53.64. So you're going to go here, you're going to try to find 53.64 as your degree of freedom. Guess what? You don't find it. So what do? What's our rule of thumb? Use the more conservative, the one that came just before it, so 50. And we're going to slide on across until we're above 99%. So 99% is over here. Slide across, and there it is, 2.678. That's our figure that we're going to put in here. 2.678, and we got it, right? Okay, conclusion. We are 99% confident the interval 0.030, what are we talking about here? Weight and grams, okay, grams to 5.9 grams. I don't know why I have that. We're 99% confident the interval from 0.3 grams to 5.9 grams captures the true mean difference. Nope, that's not right. It's not the true mean difference. It's the true difference in means between the weights of food eaten. Yes. Okay, we're 99% confident that confidence interval gives us. So then if the question came up, do we think that the cat eats the same amount? I'm going to say no, because 0 is not included in my interval. So I actually think that he eats more of one than the other. And actually we'd go and see, it looks like Tabbycat. It looks like this cat likes Tabbycat. Okay? There's a panic problem. Okay, so here's the next question. Suppose we want to test the hypothesis that the mean Tabbycat eats is higher than the mean of Chow Lion she eats. State the null and alternative hypothesis. Okay, so something you should know. Null hypothesis, always a standard. And we're going to say this. We're going to say the mean of Tabbycat is equal to the mean of Chow Lion. Okay, or if you like to put it another way, Tabbycat minus the mean of Chow Lion would equal 0. Okay, and then alternative hypothesis to this one. So we want to test the hypothesis that the mean eats is higher. There it is, right? So Tabbycat is higher or greater than, a bigger weight than Chow Lion. Tabbycat minus Chow Lion is greater than 0, right? Gives us a positive value. So that would be it. That would be the null hypothesis if we wanted to use it. And then as we go on to the second example, no, I guess that's it right there. Okay. So if that were the case, let's just think about what this means. Now we just looked at, like, is this in here? The answer is no. So we would anticipate rejecting the null hypothesis at the 1% level. So we're always going to be, right, the alpha level that we would use here is always going to be the complement of whatever your confidence interval is. Alpha level 1%, then I would think a confidence level 99%, right? Something like that. But let's say that, so this would be the H in it. The A, I'm just going to work this out a little bit more to you. The A is going to be the exact same A up here, so we don't really need to double up on that, right? So the A's are going to match. The T, let's talk about the T. So since I'm doing a T distribution, and it would be centered around, guess what value? 0 because the claim is always the center. And then the value that I would be looking for here on this is going to be 85.2, that's x bar 1, minus x bar 2 is 82.1. Let me just work that out real quick. Let me get my calculator going. 85.2 minus 82.1. So we're talking about a difference of 3.1. So I would find 3.1 on the curve, and I'm going to shade above. Why? Because I put greater than on my alternative hypothesis, right? One-sided curve. Then I would do a t-value. The t-value, remember, is always going to be 85.2 minus 82.1 minus the claim, always going to be 0, over the standard deviation, which we just wrote up there. We've written this a couple times now. 3.45 squared over 31 plus 4.62 squared over 30 and equals, we'll let our calculator equal that for us. Then we are going to find a p-value, and then we can make a decision and do all that. So let's do our calculator. Let's go to test. Let's go find this 2-samp t-test, right? Instead of doing a t-interval, let's do t-test. 2-samp t-test. Stats, we still got the same stats in there. Yes, it's got it all for me. I need the greater than sign. Pooled, no. Again, if you don't, just say no. Just say no to pooled, okay? So say no to pooled. Let's go to calculate and check this out. I get a 2.96 as my t value. Degree of freedom is still 53.6, right? So it's a weird degree of freedom, but let it go. Let it go. P-value is 0.00227. So what are we going to do with such a small p-value? We make a decision. We would reject the null hypothesis. Now, if we weren't given an alpha value, we'd just say what alpha value we're using at the 1% alpha level. In summary, we'd say we have statistical or significant evidence. Evidence. Gosh, come on. Evidence to suggest that the mean amount of Tabacat is greater than the mean amount of Chow Lion. All right, so there it is, right? So doing the same thing, think proportions, exact same setup that we did yesterday, applying it to means. So what does it mean? It just means doubling up. We're going to have to check both populations, right? Make sure everything works, put a lot of values in there, right? But let your calculator do its job. Its calculator will really, really run this thing, okay?